All right, let's dive right into this explainer and demystify the abstract magic behind C++ objects. We're going to look directly under the hood at how the compiler actually handles them. If you've ever written a C++ class and wondered what invisible strings the compiler is pulling to make everything work so seamlessly, you are in exactly the right place. So here's our roadmap for today. 1. The magic of abstraction. 2. Arrays of objects. 3. The hidden this pointer. 4. Static members. And finally, number 5, copy constructors. Starting off with section 1, the magic of abstraction, building the conceptual chassis. The absolute crucial point here is that an abstract data type, or ADT, lets us hide all the messy implementation details. It gives us this really clean structural chassis to work with. It's kind of like driving a car, right? You know exactly how to use the steering wheel and the pedals, those are the logical properties, but you definitely don't need to understand the exact fuel injection mechanics, the implementation details, just to go get groceries. This separation is what we call information hiding.
And it's brilliant how C++ handles this abstraction, technically. Now, while C++ did expand old-school C-style structs to have functions, constructors, and destructors just like classes, there's one major default difference. Classes default to private members. They enforce that information hiding by default. Structs, well, they default to public. So as a general rule of thumb, you really only want to use a struct when all members are public and you don't have any member functions. If you need privacy and logic, you build a class.
Moving right along to section 2, arrays of class objects, scaling up our engine.
When we declare a standard array, let's say we call it array of objects 1 that holds 3 point objects, the compiler has a job to do. It has to actually construct them. Because we aren't passing specific arguments here, the class absolutely must have a default constructor ready to handle that initialization.
And sure enough, that default constructor kicks in and cleanly initializes every single point in our array to 0. It just fires off that default setup sequence for each individual object right down the line.
But here is the thing. What if we don't know the exact size of our array at compile time? What if we need to manage memory dynamically? Hard-coding an array size of 3 isn't always going to cut it in real-world applications, where data scales up unpredictably. To handle that kind of dynamic scaling, we use a pointer along with the new keyword. That lets us allocate our array directly on the heap, the system's pool of dynamic memory. But here is the absolute most important part. Because we manually requested this memory, we have to be good citizens. We have to give it back using delete square when we're done with it. But just like our static array, that default constructor fires off anyway and initializes our dynamic points perfectly. So whether you're going static or dynamic, the C++ compiler is always making sure your objects are constructed before you can even use them. Section 3, the hidden this pointer, the invisible wiring. I want you to think about this logically for a second. If you have 100 different point objects floating around in memory, and you call a function like getX on just one of them, how does the function actually know which object's x coordinate to return? Well, the secret is the this pointer. Every single time a member function runs, the compiler secretly passes it this hidden wiring, so the function knows exactly which object it's acting on. So when we actually call p1.getX, the compiler secretly translates that behind the scenes. It passes the memory address of p1. Then, right inside the function definition, it intercepts that address. When we write return x, the compiler implicitly interprets that as return this-x. It's following that hidden pointer straight back to p1's specific data. Next up, section 4, static members explained, shared global resources. Now, normally, every object gets its very own copy of a variable, but a static data member is a totally different beast. Even though something like a count variable is defined inside the class, it's actually initialized outside of it. Unlike normal variables, static data members exist completely independently of any object. They are essentially a hybrid between a global variable and a class member, meaning all objects of this class share that one single count variable. Which brings up a really fascinating mechanical question. How do static functions actually operate? If they're shared by everything, how do they know who is calling them? The short answer is they don't, because static functions are associated with the class itself and not any specific object. You have to call them using the class name and the resolution operator like test.count. Since there's no specific object involved in the call, there's no this pointer to pass. As a direct result of that, static functions can only access static data members. They are completely blind to individual object data.
Finally, section 5, demystifying copy constructors, the critical climax.
The compiler tries to be super helpful here. It provides a default copy constructor that automatically triggers in 3 very specific situations to do a member-to-member copy. Whether you are initializing a new object with an old one, passing an object into a function by value, or returning one, the compiler steps in to just duplicate the data.
Under the hood, this default copy takes the exact values of x and y, say 10 and 3, from our first object and wires them directly into our second object. Now, this member-to-member copy works absolutely flawlessly for simple data types, things like integers or floats. But this default behavior is actually hiding a massive trap.
See, if we have a class with a pointer variable, letting the compiler do its default member-to-member copy means it literally just copies the memory address. That means both objects now point to the exact same dynamic memory. So when the first object gets destroyed, it deletes the memory. Then the second object tries to delete that same memory again, and boom, you get a total runtime crash. The fix? We have to write a custom copy constructor that intercepts this whole process, allocates a brand new dynamic memory buffer for the new object, and then copies the actual characters over safely.
So, the absolute key takeaway here, the one thing you must remember to keep your engine running without crashing is this. If your class has pointer member variables, you have to manually write the copy constructor. You just cannot rely on the compiler's default shallow copy, which blindly duplicates memory addresses. You have to take manual control to ensure deep copying, physically duplicating your dynamic resources.
We've seen how the compiler manages arrays, how it sneaks the this pointer into our functions, shares static memory, and handles object duplication. It is just an incredible piece of machinery. But honestly, it makes you wonder. If this is the level of work happening just for a single class, what kind of chaotic, invisible magic happens under the hood when we start stacking these classes together in complex inheritance hierarchies? Well, that is a topic for another explainer. Keep coding and keep looking under the hood.